networks, those two networks. In that we are going to see field net, having net, bidirectional associative memory. Okay, this is called as recurrent networks. Okay, and by coming non-recurrent delta root back propagation network is there. We have seen that back propagation. Okay, and if we come into recurrent networks, we come into the unsupervised recurrent networks. Carpenter Grossberg, we are going to see this network. We come into non-recurrent of unsupervised coherent self-organizing MEM. That is a coherent network is there. Okay, so what happens? So these are the four networks. Main this can be categorized into supervised and unsupervised. But if you take the counter propagation, yes, we are going to see all the networks for 4 training slides. So now we are going to counter propagation. Counter propagation is nothing but semi-supervised. You can say that supervised or unsupervised. Okay, one part belongs to supervised and another part belongs to unsupervised. That is called as semi-supervised learning technique. Okay, semi-supervised learning techniques. Okay, so how you are saying that? Supervised or unsupervised. Okay. Okay. So yes, the one part of the layer is belonging to supervised. Another part of the layer is belonging to unsupervised. So CPNS network, a counter propagation network that learns a bidirectional mapping in hyperdimensional space. Okay, bidirectional mapping means yes. Okay, if you have any problem, we have input layers, okay, output layers, and parallel we have hidden layers. Okay, what happens? So this is linked like this, and this is linked like this. Okay, and this control is linked to this type of category. What happens? So here we are able to say this is supervised and this is called as unsupervised. This is unsupervised, this is supervised. Notice that there is some predefined and some predefined descriptions that okay, this should be supervised and this should be unsupervised. Okay, this is what we are going to see diagram. What happens? There is a bidirectional. If you are not able to find that things, okay, if you are not able to find the things, what happens? Yes, we can able to adjust the weights by ourselves. Okay, there is a bidirectional mapping. And CPN is a multi-layer network based on a combination of input, clustering, and output layers. Although this network uses linear neurons, it can learn non-linear functions by means of a layer of continuity. For example, take the back propagation. What is the learning function here? Non-linear or linear? Non-linear. This is non-linear. This is linear. This is linear means what type of function this is? Radial basic function. Good. So what happens? So it can deal with fully non-linear. Although this network uses linear neurons, it can learn non-linear functions by means of the layer of unit means. Yes, as like back propagation, the function should be non-linear. The learning function should be non-linear. Okay. Then CPN learns both forward mapping from this is called as n space. Okay. So CPN learns both forward mapping from n space to n space, and if it exists, if it needs, again, the inverse mapping from n space to n space for set of parameters. For example, if you capture the image, yes, if you capture the image, what happens? Getting here, the image will be getting here. That image will be, again, should be the blurred condition, blurred. If you are not able to get the image in the blurred in a very different manner, what happens? So if you take the back propagation, what are you going to do? Yeah, what are you doing? What have you done? If you take the back propagation, what have you done? You are filling the input. If you are not getting the output, what are you going to do? The back propagation, the radial distance, what have you done? So synaptic weights will be adjusted. Am I correct? Synaptic weights will be adjusted. Okay, but you do not check again so the input is correct or not. But if you come to this side, this category, yes. So CPN learns both forward mapping from n space to m space. Think of it as n space, this m space, and it takes the and it captures the final image and we check it. Final image should be the proper weight. If not, what happens? Try to change the weights to get the clarified image. Again, if not possible, means it once again checks whether the image should be in the proper condition or not. Okay. So in the back propagation, it is not possible. The back propagation, what are the inputs? We are giving the 2 numbers or 3 numbers or random numbers. Yes, we cannot be able to stick it here. But here, once the image, we capture the image with cameras, okay, and this processed by networks, and if we are not able to get the final output means we can check it by checking the synaptic weights, so we can able to get the different image or not. Even though we are not getting the image, what happens? Once again checks it, that it comes from reverse from this to here. Okay, checking whether the image should be in the proper way or not. Okay, whether the accurate image should be in the proper way or not. Okay, accurate image means whatever the image occurred, want to process and we get the final image. But the final image, if not get properly, again we check it. Okay, whether the accurate image is in the proper way or not. Okay, so sometimes the accurate image is in the proper way, but at the time of processing, the accurate image will not be processed properly. What I am saying that yes, I captured the image. Okay, so I want to process the image by a counter propagation network. So finally, I am getting some blurred image. I have changed the synaptic weights, but still I am not getting the image. What happens? The layer which is in this side will check this again. Whether the image is in the proper condition or not. Okay, so sometimes image will not be in proper condition. What are the accurate image? Yes, you can able to view at the time of processing. At the time of processing means yes, you are giving the image as input here, but this input will not be properly fed into the network. What I am saying that if it is properly fed, you can able to get the defined image. If it is not properly fed, even though you are trying to adjust the synaptic weights, okay, you are not able to get the defined image here. Okay, so that's the thing. Again, we'll check it. Whether the fed image is in the proper way or not. Okay, that's the thing. Reverse mapping is possible here. Next, the network is able to learn a function and its inverse at the same time. What's the thing? So it's able to learn a function, and if you not able to get the defined image, yes, its network is having the probability to check the field image proper in the proper condition or not. Okay, application is compress data, approximate functions, and observe patterns. Okay, that's the image processing. You can able to compress the data, and you can able to extract the image. Okay, all the things are possible. Okay. Okay, sir, this is your counter propagation network. This is your counter propagation network. Yes, yeah, I have three layers: input layers, hidden layers, and output layers. Okay, so hidden layers, counter propagation network is unsupervised winner. Take all the competitive learning network. Okay, what in by unsupervised winner or semi-supervised winner? We can say. Learning process consists of two phases. First one is unsupervised phase and supervised phase. Okay, so unsupervised phase means concurrent learning, and supervised phase means Grossberg learning. What I say that it is semi-supervised. It is a combination of unsupervised and supervised. Okay, so what happens? So concurrent learning phase comes into unsupervised phase, and Grossberg learning comes into supervised phase. So some part will be related to unsupervised, and some part will be related to supervised. Okay, so these are input layers, these are hidden layers, these are output layers. Okay, so in the output layers, what happens? In the output layers, what happens? You get the image. Okay, you are not able to get the image in all the output layers. You are not able to get the image in all the output layers. You can able to, for example, yes, I can able to get the image that neuron and that neuron, but you can segregate this neuron is best. That is called as winner. Okay, I have already discussed in the previous introduction class. Winner neuron, winner learning function. Okay, winner competitive learning. That means yes, we have to train. We are taking the image and it is processed and finally getting the output. Okay, and finally getting the output. So in the output, the image should be like this. In parallel, we are having dogs, we are having some course, we are having some cats. What happens? So these two pictures will be enhanced properly, and this picture will not be enhanced properly. Or some pictures will be able to see exactly, and some pictures will not be able to see exactly. Okay, or what happens? These two pictures coming under one neurons, and this picture coming under one neuron. Okay, what happens if you can able to see these pictures in a clarity manner? Yes, this neuron is the winner. You can able to see this is not properly. This is called as loser. Okay, that means what are neurons succeeded? So what are the pictures coming in adopting under neuron? If it is succeeded, that is called as winner. Okay, that means you can able to see the image in the clarity manner. If not, means you are not able to see the image in the clarity manner. Okay, yes. So this is a fine architecture. Yes, we can able to see here exactly concurrent learning and Grossberg learning. What is the concurrent learning? Whether it's supervised or unsupervised? Unsupervised. Grossberg learning is supervised. So, okay, unsupervised and supervised. Understood or not? So, okay, what is by unsupervised and what is, can you able to differentiate the supervised and unsupervised? Can you able to differentiate the supervised and unsupervised learning technique? Unsupervised means what happens? It's self-learning. Supervised means teacher want to teach the thing. Ask what their agenda, be quiet, otherwise if it's unsupervised learning, what happens? Abhijit is very much interested to carry out the interaction just like what he carried in the parliament. Am I correct? Okay, good. So, unsupervised and supervised learning technique. Yes. Recurrent learning, cross-learning learning. Yes, we are going to see in the forthcoming slides. So, what's the difference between unsupervised learning technique means? Yes, unsupervised means yes. So, here I input what is the cluster similar to the self-organizing map without neighbor. Supervised means weights from the cluster units. Here, cluster means nothing but what I said. So, all the input vectors, all the input neurons are clustered and giving the signals to the hidden layers. So, weights, all the what happens in this hidden layer? Again, weights from the cluster means weights from the hidden layer. Okay, weights from the cluster and hidden layer. It stands for the output units. Okay, or adapter to produce the desired response. Here, unsupervised means what happens? There is no rate of teacher. Whatever is happening, it's coming outside. But supervised means yes, whatever is coming from the unsupervised. So, as a teacher, or as a programmer, as a network manager, you can able to control the things. For example, if I have any problem in the image, yes, first I can able to bring the synaptic weights here in the cross-learning learning. Okay, that is supervised learning technique. Okay, after that, so write the synaptic weights and then get the image. That is called as multiple image. Even though I want able to get that defined image by the synaptic weights, then I come to this side, recurrent learning. Okay, but even though it's unsupervised learning, you cannot able to touch anything. So you cannot able to touch anything this side. What happens if you are not able to get the defined image here? Okay, yes, we are trying to change the weights. Okay, and again it's coming to taking the images processed here properly. Okay, if you get the image, if you give the image like this, okay, what will happen? This image will be segmented. Okay, and these 3 neurons will process this image, and these 3 neurons will process the image, and these 3 neurons will process the image. Okay, and finally get the defined image here. Again, this is process, and finally getting the image is there. Not able to get the defined image. For example, if you have any color problem or any some other problems on that, yes, you can able to change the weights. So the weights is that red, blue, color. For example, if I diminish the red color and you can able to give the image, yes. Or you can able to diminish or increase the clarity of the blue color, and this clarity, if you see the image, yes, it's possible. But what are things can able to be here? If you want to get the defined image, yes, you can check it the image is properly processed or not. Therefore, this unit. Okay, if it is not properly processed, what happens? There is no chance to change the weights here. There is no chance to change the weights here. That's like what is done here. Understand? This is supervised learning technique. Okay, we can change the weights, we can change the intensity of the light or diminish the intensity of light. Okay, if not possible, yes, we can change that. We can check the processing of this side, processing of the image. Okay, so we can check the image here. Okay, if not means again it jump to here only. We are not able to touch here. We cannot able to touch here. Okay, that's called as difference between a supervised and unsupervised learning. Okay, sir. Okay, sir. So the diagram calculation you can able to see input layers x1, x2, x1. Hidden layer is also called as cluster layers. Okay, and hidden layer is called as named as h1, h2, and hm. Output layer is called as y1, y2, and ym. Weights and transfer function. Okay, we can use the transfer function for linear. Okay, so the final transfer function should be a linear. Okay, and can able to handle the non-linear sections also. Coming to phase 1, it is called as learning, unsupervised learning. It computes the equidistant distance between the input vector and the weights of each hidden load. Okay, so input neuron is there and hidden layer is there. Okay, so what happens? Okay, as like this is correlated this thing. So computes the equidistant distance between the input vector and the weights of each hidden node and find the inner node with the shortest distance. For example, what I am saying that the try to observe this thing, I can explain this just to some sample diagrams. Then adjust the weights that connect to the winner node in the hidden layer. Sometimes I can compute the distance. Okay, so compute the distance, shortest distance, and find the winner node and try to adjust the weights of the winner node. Okay. Now you say this. Now I will show this. Okay. So you can think of it as one of your structure of the quantum propagation. You can able to think of it. Okay. So H1 this indicates hidden layers. All hidden layers, hidden layers, hidden layers, hidden layers. And this is called as input layers. Okay. What I am saying is, so one neurons, this input is hidden layer is that, second layer, third hidden layer, first hidden layer is that, and parallel we have one input layers. Okay. This diagram shows a sample system hidden layer and a sample into the network. Okay. In this example, hidden layer. So you can able to find here. Second hidden layer is right side. If you look at the positive side of the right side, what happens? You can able to find the x1, y1. Okay, if you come to the side, next slide, you can able to view hidden layer neuron x2 means according to the learning rules move closer towards the current input network. For example, so we have the image. So think of it, we have the image. That image, okay. So we have the image like this. Okay, so we have the image like this. So neurons are there. Okay, we have the image like this. So we have to fit that image into this neuron, pass into the neuron. Okay. So what happens? Whether this, if you fit this image in this neuron, which indicates best or not. Okay. If you fit this image in this neuron, which indicates best or not, you have to check it in each and every neurons. Okay. And you have to find which is winner. That's the thing I'm going to say. So you can able to say hidden layer is. You can able to say hidden layer of neuron x2 bits. Actually, this is here. Actually, this is here. Okay, this weight is there. This hidden layer. Okay, if you try to shift hidden layer, try to shift the neurons of the layer from here to here. Yes, that is the weighting. You can able to say, compared to this neuron with the layer, this neuron is the best. That is called as winners. Okay, so you can able to say this example hidden layer neuron H2 means according to learning rule, is moving closer towards the current input vector. That means. So it can able to adjust. This is as input, this image. In comparing these neurons in layer, if you reduce the short distance between these neurons with this side, yes, you can able to get the defined image means yes, we have to do it. We have to do. Okay, that's the thing I come here. Coming to this side, after doing through many episodes as like that. What I am saying that the input is that we have so many neurons. So you have to think of it. Which neuron is best? So many neurons are near this input, but we have to find which is best. So that's the thing here. So okay, in the last slide we are saying that I am trying to adjust from this hidden layer to this side. Okay, but you can able to find. Now you can able to find many that is many iterations. Okay, you have to initialize and carry out many iterations. After carrying out many iterations, okay, you can find out which is best. Okay, so in the previous slide you can able to find out. Okay, hidden layers, for example, second hidden layer is which first, compared to first, this, the second is very close to this. Okay, as like that, you have to carry out several any iteration as well as suppose. You have to carry out several iterations and you have to find which is best, which is winner. Okay, that's the thing we are saying. Each hidden layer will win a subset of inputs. Okay, each hidden layer will win a subset of inputs. Okay. Okay, sir. So we can able to see a small example. Yes, we have the images like this. Okay. Try to think of it. Okay. These are neurons hidden layers. These are neurons in this. These are neurons hidden layers. We have some images one or some weights like this, weights like this, weights like this. Okay. So what happens? We have to find out which is best. That 3 is okay adapted to this neurons. This 1 is adapted to this neurons. This 2 is adapted to this neurons. We have to find which neuron is best for this. For example, if you adopt this neuron, yes, you are able to get the image is good. If you adopt this neuron, you can able to get 15% efficiency. If you adopt this neuron, you can able to find 30% efficiency. But you have to find out, you have to consider all the neurons with respect to that image, and you have to find out which is best. Okay, so that's the thing you are doing. For example, you can see that That is the first project equivalent distance. So yes, I found that this is best. Okay, for this neuron I found this is best, and this neurons, this image is allotted to this neuron. Okay, and for second neuron this is best. Okay, that's the meter node, and finally for first neuron meter node is best. Okay, that is means the shortest distance. Coming to this here, yes, this is shortest distance. Okay, you can able to say shortest distance for shortest equivalent distance for this neuron. But yes, we can able to say, sir, this is very close to this. Obviously, this is the shortest distance. It's not like that. Okay, so shortest distance means if you get the image, for example, if you take this neuron and allocate this image, and if you getting the images around 50%, and if you allocate this neuron and you getting the images around 60%, means this is shortest distance. Okay, this wherever you are able to increase efficiency for the neuron, that is called as the shortest distance. Okay, so for shortest distance for the neuron is highlighted in the yellow color. Okay, and next it adopts that neurons around to that neuron. That image is around to that neuron. And then coming to second, we can able to find shortest distance, that is rounded, which highlighted in the yellow color. And then coming to next slide, that weight is adjusted to that weight or image is adjusted to the corresponding neuron. And coming to the first, yes, highlighted is that, and that neuron is adjusted to that image. Okay, that is called as winner node. Okay, sir. After that, so once if you adjust the winner node, you cannot be able to say. What I am saying is, yes, now the image is turned to the appropriate neuron. Now the image is turned to the appropriate neuron. Again, you have to tune up to get that defined image. Now you get the defined image. Okay, there are so many neurons out there, but this image is very close. If this image is close to this neuron, yes, you can able to get the defined image. Again, I want to enhance the defined image. Then defined image. If you take the tool monitoring side, or if you take the image browsing, okay, if you find any cracks in the bottle, or if you find any cracks in the component, we have to identify it. Okay, so for that this is not possible. For example, you have to enhance the image. In upgrade manner means, yes, again you have to calculate that is exact neurons. Just to think of it. For third, this is shortest distance. Okay. For third, this is shortest distance. Okay. And then this we have understood that there is a winner node for third neuron. That neuron will use that defined image. But again, you can able to find again and try to adjust the weights to get the clear difference. Even though the neurons is very enhance that image, again I want to get the exact image, 100% efficient image. So for that, so again I'm checking this. This is neuron. Why not? We're not able to find the exact neuron between this neuron to this neuron. Okay, is it possible? For example, among these neurons, I said that this is possible. Why not? It is located here. If this neuron is located here and this image is very close to this neuron, and it gives the 100% image, that is the exact neuron. So we have to find out by checking the weights. Okay, that's the thing you are saying that. So reducing the weights. You find here there is a winner node for third neuron, and then coming to this is a winner node for second neuron, and then coming to the first winner node, this is the first neuron. Okay, and again we are checking the weights of the first neuron. Okay, this is the weights of the third neuron, and this is the weights of second neuron. Okay, and finally you can check it. You can able to check it, readjusting the weights. So once I readjust the weights, what happens? Yes, try to think of it. Before readjusting the weights, even though that second neuron adopts, this is a winner layer. Yes, I can able to see the image around 95%. I want to see the image on exactly 100% means. 100% means, okay. See, that's the thing. Once we get that some 190% neuron, again you have to readjust the weights. Again, to enhance 100% image. Okay, that's the thing that we're doing here. Reduction of ED file training rate. Okay, that's one of the process. Once you reduce the weights of that neuron, okay, that image will adopt this neuron. Okay, exactly fixed on the neuron, and that neuron one leg exactly gives the 100% image when compared to other neurons. Okay, Coming to this, yes. Finally, get the second point is there. Finally, get the second point is here. The coming. So once again, do the same thing. Okay. Some days I have the problem. What I am doing that. So try to think of it. Try to leave it. Okay. Think of the third image. This is one of the image, and we have so many neurons. Okay. What happens? We have to fit. So this image. We have to note the image means this image should be 100% efficiency. So for that we have to select best neuron, that is winner neuron. Even though we have so many neurons, we have to select winner neuron. So selecting winner neuron is not possible. Okay. So what happens for that? We have to calculate the shortest distance. Shortest distance means from 3. Okay, we have to find which is the, even though so many neurons are there, among these neurons, what are neurons highlighting? We have to show that which is best among this thing. That means which neuron gives that exact image, that is around 50% or 60% when compared to other neurons. Okay, this is giving 60, this is giving 50, this is giving 55, this is giving 70 means yes. Again, you have to track the neurons, the image in the neurons here. Okay, after that we are not able to say that still it's giving 70%. What about the remaining 30%? Again, we have to readjust the weights. Okay, what are doing the back propagation of the one? Again, we have to readjust the weights. Okay, so for that only we are adopting that unsupervised learning technique. Okay, that supervised learning technique will readjust the weights automatically and find that again if this neuron, if this image adopts this neuron, that is called as winner neuron. Okay, winner neuron, that is calculating shortest distance and saying that among these neurons this is a winner. Okay, yes, these neurons will giving that. Well, we can able to view the image exactly at 70% with this neuron. That is called as winner neuron. But we cannot be able to say that is a winner, even though it's a winner neuron, but we cannot be able to say because I need the 100% image. For image processing, I want to process the image exactly at 100%. Okay, so if you take the back propagation algorithm, we can get the surface 80%. Okay, you're satisfied. Okay, it's okay. If you come to the image, I need that for image processing. I want to process the image exactly. Even though if I find any cracks in the bottom, yes, I want to find the crack in the bottom exact image. That is not possible. Okay, so that is possible for that only way. Again, once you find the winner neuron which is the best, okay, once you find which is the best among these neurons, you have taken that neuron as a reference. Okay, and again you have to change the synaptic weights. That is the supervised learning technique. We have two parts: Recurrent and Rosberg. Recurrent will fix. Recurrent will fix. That's unsupervised learning technique. Okay, will use this is a winner neuron. Okay, so unsupervised learning technique will indicate this is a winner neuron. Coming to the Rosberg, what happens? That is supervised learning technique. If you are not getting the image 100%, what happens? Try to change the weight. Okay, so once you say that this is a winner weight, okay, once you say this is a winner weight, again you want so this is a winner neuron, but you're not giving that image exactly 100%. It's giving around 90%. But I want the 100% image. What happens? Again you're going for jump into the supervised learning technique. This is a Rosberg learning technique. That technique is a supervised learning technique. What happens? It tries to change the synaptic weights. Okay, and exactly fits. So even though we have so many neurons, this neuron which is located here, it gives the exact image. That means will gives the 100% defined image. Okay, that is called as the final image. Okay, what I am saying here. So just a minute. What I am saying that here. So we are two techniques, Recurrent and Rosberg. Unsupervised learning technique indicates which is best. Okay, which neuron is best. Okay, which is called as it indicates winner neuron. Once it indicates winner neuron, okay, so we cannot able to say that is a final, that is not a final neuron. Okay, once we get the 100% image in the winner neuron, yes, it's finished. But winner neuron indicates around 90% of efficiency or 80% efficiency. Again, the image processing we have to get 100% efficiency. Okay, as found by back propagation of curve. Okay, what happens? This is a supervised learning technique. This learning technique tries to adjust the synaptic weights between the neurons. Okay, we have the neurons like this. So we have the neurons like this. Okay, in this image, what happens? This image indicates this is the best neuron. That is a part of recurrent learning. Once this is indicates this is the best, what happens? This Rosberg try to adjust this synaptic weights. Okay, try to adjust this neuron synaptic weights and find whether this is best or some other location which is nearer to this neuron. So this neuron is best. For example, yes, we can able to see the third. Okay, first this is third means this indicates this is solid solution, this is a villain node. But if you are adopting Grasper, it indicates that that neuron, that image comes here. Okay, that's a thing. So we are adopting two techniques here, unsupervised and supervised techniques. Okay, so unsupervised and supervised techniques. What happens here? Yes, this tree indicates the one of the image, and we have so many neurons. With the help of the recurrent learning, unsupervised learning technique, we can able to say this neuron is the best. Okay, so this neuron is best. If I learn this neuron, it get clarity is 70%, 75, 85, 60. Then it fit to this. This is called as inner neuron. This is done automatically. That is called recurrent unsupervised learning technique. Coming to Grasper, yes, we can able to 70%. So 100% located here, allocated here, allocated here, allocated here. Okay, for that what happens? These neurons will train by changing the synaptic weights, and means you have to change. That means you have to fix the program like that. What happens? That's supervised learning technique. Okay, as a programmer, you have to fix the thing. Okay, and parallel what happens? Once you get the image 80% here, it try to check the other neurons is nearby this area and find which is best among this thing, which gives that. For example, this gives 90%. This gives 95, this gives 97, this gives 100%. Then this image will jump from this neuron to this neuron and says this is the best, which indicates exactly the defined image. Okay, that's called as the combination of. Okay, it's called as the semi-supervised learning technique. That's called as counter propagation. Okay, counter propagation means a combination of unsupervised and supervised. Okay, one part is called as, for example, if you have any problem, this image will this image will fix automatically to this side in the neurons. Okay, therefore program learning. Okay, that's unsupervised learning technique. Okay, and so that this is a winner neuron. Once you find that winner neuron is this, okay, and you can able to find among this neuron, this winner neurons means apart from this neuron you have so many neurons. Okay, so that neurons will indicates 100% image when compared to the winner neurons. Winner neurons gives 80%. If the neurons located here, it gives 100% means that is the process of Grasper. What happens? The Grasper will, once you get the winner neuron, the Grasper will try to change synaptic weights with the help of the neurons and find. So this neuron which is near to this neuron is the best for this image. That's the thing. This image is located in this neuron. Okay, that's the thing I'm saying. Yes, you can able to find here. This indicates first. This indicates the direct indicator. Yellow direct indicates the winner neuron. That's of the program learning, unsupervised learning technique. Coming to this thing, yes, it's coming nearby. As like that, we have to carry the process for first, second neuron. Once it is finished, yes. Once it is winner neuron is announced, what happens? After that, program learning is finished. Grasper learning is started. Okay, Grasper function is started. Once the function of Grasper means, what happens? The Grasper will start to change synaptic weights and find which is the best. Okay, that's the thing. Reducing the weights of first neuron, reducing the weights of second neuron, third neuron. Okay, and parallel is again reducing the weights. Okay, like this is going on. Okay, and parallel for second neuron is going on. Okay, and finally that's a thing. So after Grasper, they reach the weights. Yes, we're getting the images. Even though in the program learning, it is the best. You can able to find. Okay, this neuron is best. Means yes, the young neuron in here. So in that neuron, the image is fitted here. It indicates that this image is very clear and precise for this neuron only. If you use this neuron, okay, this neuron only indicates exact image of the product or exact image of the system. Okay, so as like that, what happens? If you feeding images are splitted. Okay, images splitted. For example, if you have red color images, blue color images, yellow color images, all the images splitted and then processed, and you can able to get the different output as like this. Okay, red color images, for red color, this neuron is best. For blue color, this image is best. For yellow color, this image is best. Okay, as like that, we can able to segregate. Okay. Because again, if it is that again, if it continues, it's a problem for me. We started, and that function itself, that module itself, trying to find the shortest distance, okay, and parallel. What happens? It indicates the winner neuron, okay? It indicates the winner neuron. So 1, 0, 1 means winner, then it stops. Again, it not stops. Understand or not? Boss, just to understand, okay, just to listen here, then you can able to understand, okay? For example, this is the image, behind so many neurons are there. Actually, this is a winner neuron. What happens? First, this image will start to fit for this neuron and say that this is 0. Okay? Again, this image will want to fit for this neuron. If it's 1, that's called as winner neuron. Okay? So, as like that, this image will want to check all the things, and which neuron is coming under 1, that is called as the winner neuron. If it's 0, again, you have to carry out the process until you find out the winner neuron. That's the thing you are saying. So, start up the thing, assign weights, training will be started, and equal distance will be find out, and if it is 1, that is called winner neuron. If not, again you have to readjust the weights until you get the winner neuron. Okay, that's the thing I am saying. Okay, this is a major algorithm. Okay, coming to cross supervised learning. Yes, once if you get the winner node, then you want to find the exact neuron. Once you find the winner neuron, you want to find the exact neuron. Okay, yes, you let the link winner node. Think of it. Let the winner node connect to the output node is set as 1, other node is set as 0. So once you find that this node is the winner node, the remaining nodes are all, okay, we need not, okay, so we will not bother about the remaining nodes. We want to bother with this winner node, and with respect to this winner node only, we want to find out the neurons. Understood or not? We want to find out neurons which is located near the winner node. What I am saying that this is the image, this is the neurons, okay, and this is the winner node. Yes, this is not needed. The reference to this winner node, we have to find out which is the neuron, which neuron is exactly suited for this image. So we can able to find this neuron, we have so many neurons with that. We have to find out. Okay, so for that is called supervised learning technique. So we have to change the weights. You have to, as supervisor, you have to fix that. For example, 8 neurons, 10 neurons, 20 neurons, 40 neurons, 60 neurons. As like that, you have to fix. This is the winner neuron. So around this winner neuron, we have so many neurons are there. Okay, we have to readjust the weights. That means you have to readjust the synaptic weights, as like what is done in the back proportional algorithm. Okay, and finally you have to say this neuron is best. What happens? That's the thing you are saying. Let the winner node is okay, connected to the output layer, and you have to find the defined image until you find the best neuron, which is located near the winner node. Okay, that's the thing you are saying. Let the link winner node is connected to the output layer is set as 1. The remaining nodes are 0, and again you have to start to train by adjusting the weights of the winner node until you get the defined image. This is called as positive image for 70% image. You have to get 100% image. For yes, it is possible. Sure, it is possible, but it is located in and around this neurons. You have to find. That's a job of your supervisor. Okay. So for that you have to change the weights. Yes, if it wins, you can able to find the 100% defined image. You can able to get the 100% defined image. Okay. That's algorithm here for best work supervised, supervised learning technique. Input training method is that compute step and 4, 5, phase 1 as I got it done here. Train and get the defined output. You have to train this neuron. You have to train this. You have to train this neuron by varying synaptic weights, and you find this is best. Yes, which indicates 1 means that is best. Which indicates 0 means again you have to train for another neuron. If it indicates best, yes. Understand not? Okay. So repeats 1 to 4 until the array is minimized, until you find the exact super winner neuron. So you can say the winner neuron. If you come into gross weight, you can say the exact winner neuron. Okay. So you can repeats 1 to 4 of phase 2 until the array is very small and stable. Very small means so we have to process the image. We are not processing any readings. So you have to process the image. Okay. So you have to get the defined image. Not this is a problem for you. That is called stability. Okay. For number of training cycles reached. Okay. So we are two values, open-end and cross-work. Open is equal to unsupervised, cross-work is equal to supervised. Okay.